All right, friends, here is part 2 of Lewis structures for covalent compounds. If you do not consider yourself a beginner with covalent compounds, then this is the video for you. If you think that the ones you've been doing in class are a little boring and you're just ready to take the quiz, maybe you don't need to watch this video at all. Probably still good if you want a little bit of extra practice before the quiz, but not required viewing for you, I guess. Okay, let's jump in with sulfur dioxide here. Remember that our first step is to count up the total number of valence electrons in the compound. So I got a sulfur and 2 oxygen atoms here. I know that sulfur has 6 valence electrons, and so does oxygen, actually. But I have 2 oxygens, so that's going to be 12 plus 6, or 6 times 3, however you want to think of it. And that is 18 total valence electrons in this compound. So I need to make sure that when I draw my Lewis structure, I don't draw more than 18 electrons, or 18 dots. The next step, of course, is to decide which one of my atoms is going to go in the middle of the molecule, and I'm going to do that by picking the least electronegative one, so the one that's farthest away from fluorine. Looks like sulfur is the one that's farthest away from fluorine, since oxygen is just like right next door. Yeah. So then sulfur is going to be the one that I put in the middle of this molecule. And I'll put my oxygens on either side, like that. Let's move this guy closer. Okay. So now that I have my my atoms arranged, I need to actually bond them together, because right now they're just like atoms kind of floating in space, not really connected to anything. So let's go ahead and put 2 electron pairs like that, and that is actually going to have the oxygens and the sulfurs be bonded to each other. Now, how many electrons have I used so far? I've used 4 of the 18 that I had, so I have 14 left to play with here. I need to draw those 14, so I need to have 18 dots drawn. Let's go 2, 4, 6, 8, 10, 12, 14, and now I'm out. Note what I did there. I started with my outside atoms. I made sure that each of those was happy before I went into my central atom. That's just, it helps. It'll help with the steps later on if something goes wrong. It's easy to tell what happened. Always do that. Good rule of thumb. So as you can see, I was able to make my outside atoms happy here. They each have their octet, but my sulfur does not have an octet, so I need to make one of these into a double bond. Now, quick question for y'all. I ended up with my Lewis structure looking like this, right? But could I have decided that I'm going to have this oxygen do the double bond instead? What do you guys think? I totally could have, right? And in reality, what's really happening is we kind of have the molecule switching back and forth really, really fast, going back between this happening and this happening. Is kind of what's going on here. Really, they're kind of both happening at the same time, and the actual molecule is kind of an average of these 2 structures. So I guess we would really have, like, instead of 1 single bond and 1 double bond, we would have 2 1.5 bonds. But normally it's not drawn like that, because it's simpler, I guess, to communicate that this or this is happening. In essence, we have a double bond and a single bond, but there's different ways to represent molecules, and that's, I guess, sort of what I'm getting at here. If this were a more advanced chemistry class, then it could, or I could totally ask you to, like, on the test, draw both of these, like both possibilities, in order to get credit. And this is how you would do it, with these brackets around it, and then the arrow showing that it's like, quote unquote, switching back and forth in between. And these are called resonance structures. Resonance structures. Some molecules have resonance. And so if we were drawing like the most complete Lewis structure, we would need to show all resonance structures. In this class, I really don't think it's necessary because we're just kind of scratching the surface of covalent bonding and single bonds and double bonds. So I haven't really spent a lot of time on resonance, but if you've been wondering, how do I decide which oxygen should do the double bond, it doesn't matter. If you wanted to be super like completionist, you could show me all the resonance structures, but I'm not going to require that on any kind of test. So that is perfectly fine with me, just like that. Okay, let's jump over to phosgene, COCl2. Now, be careful here because this is a carbon, an oxygen, and 2 chlorines. This isn't a cobalt. It's not a CO. It's a big C and a big O, not a big C and a little o. So that's phosgene. If you want to pause this one and try it yourself, or pause the video and try this one yourself, do that, I guess. If not, here we go. So my carbon first has 4 valence electrons plus 6 from my oxygen, and then each of my chlorines has 7, so it's going to be 7 times 2. So then 14 plus 10 is 24 total valence electrons. Which atom is going to go in the middle? That's going to be my carbon because it's the least electronegative. And then we can put my Cl's on either side, and I'll put the oxygen on top. If you did this a different way, that's totally fine. This isn't even actually like super accurate to how it actually is, but that is okay. Again, these are just 4 atoms floating in space, so let's put in those bonding pairs. Always the first electrons that you add is actually bond the atoms together. And then with the ones that we have left, with the electrons we have left, we're going to fill in as many octets as possible. Real quick, one thing that I was seeing walking around the room was that people were doing kind of this thing where we would give like Cl, we'd give that guy an electron pair, and then we go across here and give him an electron pair, and we kind of do this like ring around the rosy thing. Don't do that, because you might end up with like multiple atoms not having an octet, and then you're not going to know what to do, or like what double bonds to make. It'll be easier for you if you focus on one atom at a time. So I'm going to focus on my chlorine here on the left, and I'm going to give him all 6 that he's lacking to give him his octet before I move on to another atom. Okay, so then I can give this guy his, and my oxygen, I can give him his. And I think I've spent all of the electrons that I have now. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yeah, so that's all 24 valence electrons spent already. But not everyone has an octet. This carbon does not have an octet yet. So pretty simple. We need to take one of these electron pairs from oxygen and move them down here, make that into a double bond, and now carbon has his octet. Everyone's happy. Now, if you were drawing your Lewis structure and you decided that you wanted to give one of the Cl's the double bond, would that be correct? I know you're probably wondering. Technically, no, but also technically yes. Let's see. I know from taking more chemistry classes than you have taken, I know that the oxygen is more willing to take that, to make 2 bonds than chlorine is. If you look at enough Lewis structures and do enough of them, and I guess study chemistry long enough, you will learn that chlorine rarely makes 2 bonds. And if something needs to make 2 bonds here, it's going to be the oxygen. There are, I guess, like valence shell reasons for that. We'll get into this a little bit with ionic bonding, but the fact that oxygen is happy with a 2 minus charge, whereas chlorine is more happy with a 1 minus charge. That sort of means that oxygen is more willing to make 2 bonds than chlorine is. If that's gibberish to you, don't worry about it. It's really okay. But basically, because of resonance, both structures are fine. But this one is going to be like more common. It's going to be more stable. This is something that's called like the major contributor. This exists more often than this exists. They're not like, this one's technically right. It does happen, but this one is more common. And if you look up the Lewis structure for phosgene, you're going to find the double bond on the oxygen, not on the chlorines. Would I count it wrong if you put the double bond on the chlorine on the test? Honestly, I probably wouldn't even ask you to draw phosgene. If I were a chemistry professor, I would count it wrong if you put the double bond on the chlorine, but we haven't learned that yet. So, yeah, I wouldn't put myself in that position of asking that question. Anyway, let's move on to hydrogen cyanide. This is turning into a longer video than I wanted it to be. Sorry. Okay, so let's go through this pretty quickly, because we've done this one like 4 times, I think, already. Let's do it again. My hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5. So that is 10 total valence electrons. My carbon is the most electronegative. I keep doing that. My carbon is the least electronegative because it's the farthest away from fluorine. I guess hydrogen's way over here. So hydrogen is fairly electronegative. Sorry. Hydrogen is not very electronegative, but there's that rule, right, that we never put hydrogen in the middle. So even though it is the least electronegative, technically, it can never go in the middle. So that means that carbon has to be our central atom here. So I'll put my carbon there and my hydrogen on this side and my nitrogen over there. Let's put in those bonding pairs, and I've spent 4 of my 10 electrons. I have 6 left. Remember, hydrogen is happy, so he's happy with 2, so he doesn't need an octet. I'll give my nitrogen these 6, and oh shoot, I'm out of electrons. 2, 4, 6, 8, 10. And my carbon only got 4, so I need to ask my nitrogen here if he doesn't mind sharing an electron pair there. And I can't ask my hydrogen atom to share another pair because he doesn't have any more. So the nitrogen's going to have to suck it up and share another pair still. If I can do this, hold on. There we go. That's kind of sloppy. But now we have it, right? Because we have our carbon sharing a lot with our nitrogen here, but that's how he gets his 8. 2, 4, 6, 8. My hydrogen has 2, and my nitrogen has 8 as well. That's the only way that everyone can get their octet, and that is the Lewis structure for HCN, hydrogen cyanide. Like that. Let's put that lone pair there. Okay, next is another 3-atom or 3-element compound here, nitrosyl fluoride, NOF. First, we need to count up our valence electrons. That's 5 from the nitrogen, 6 from the oxygen, and 7 from the fluorine. So that's 11 plus 7 is 18. 18 total valence electrons here. Which one is the least electronegative, farthest from fluorine? That's going to be my N. So I'm going to put my N in the middle. My fluorine on this side and my oxygen over there. And then we can put in our bonding pairs. I've spent 4. I have 14 left. Let's go around. Give everyone an octet until we run out. 2, 4, 6, 8, 10, 12, 14. Uh-oh. I'm out of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. I was wrong, sorry. Okay, so now that's all 18 spent, and I was able to give everyone an octet except for my central atom there, nitrogen. So now I need to ask one of my outside atoms to share another electron pair, right? I can either ask my oxygen here, or I can ask my fluorine. If we go back to what I was saying with the phosgene, the oxygen is more ready, I guess, to make a double bond than any halogen would be. Because I remember I said that chlorine, because it's in this row here, sorry, because it's in this column here, it only wants to make one bond. It's not really looking to make two bonds. This oxygen is more willing to make two bonds. So that's why it's actually going to, that's why it is going to make the double bond with nitrogen rather than fluorine doing it. So that would be the answer here. O double bond to N, single bond to F. And let's put in our lone pairs here. Cool. And that's how we get all of our octets there. Okay. This was a 16-minute video to explain these 4 Lewis structures. Should not have taken that long. Sorry about that. But I'll be making part 3 here in a second, so both of those will be going up tonight. Let's see. Yeah, I guess that's that. Have a good night, or a good evening, or morning, whenever you're watching this. I have no idea, obviously. Okay, bye.